Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver, and today we're just going to look at a few simple harmonic motion questions or periodic motion questions, a few systems. So we have a spring, right, a mass attached to a spring here, a pendulum question, and then a wave traveling on a string. All these are periodic motion questions. So let's get started. For this first one, we have a mass attached to a spring where that spring has a spring constant K and a period T and a certain amplitude. And the question just asks us if A is doubled, right, whatever that amplitude is, it could be any number, right? If it's doubled without changing T, how would Vmax and Amax change? Well, first we can look at period, right, and see what period consists of. You know, we're not changing period, so we really don't have to worry about that. So we can see that really omega, right, if period doesn't change, omega is really the thing that dictates period, so omega isn't changing, right? So when we look at the equations for Vmax and Amax, right, where again, if you're wondering where these equations came from, go watch the concept video. I did the concept videos on how to get these equations, how to derive them, all of them. So I'm pulling this from that video. It's also from your equation sheet, but we know Vmax for periodic motion is written like this, and we know the max acceleration is written like this for periodic motion. So if we were to double A is right there, right? That's the amplitude. So if we double the amplitude without changing T, how would Vmax change? Well, if we double A, right, Vmax is going to double because A isn't squared or anything. Amplitude is just amplitude. So if we double amplitude, and omega is not changing, then that means Vmax would double, right? If they were both changing, maybe something different would happen with Vmax. But if we just double A, Vmax is just going to double because Vmax is only based off of omega and A. And if omega isn't changing, which we determined because T isn't changing, and A is the only thing changing, you double A, you double velocity max. And with acceleration, the same thing. It's based off of, right, that A right there is amplitude, right? It's not squared or anything, amplitude, right? We know, and we know omega is going to be the same because period doesn't change. So if we double amplitude, the max acceleration would also double. So they would both double because amplitude is in there. And if you double amplitude and not change omega, then the only thing that's going to happen to this value is it would also double. All right, so B, if T is doubled without changing A, how would Vmax and Amax change? Well, this one's a little bit more tricky because we kind of got to see something here, okay? So if T is doubled without changing A, how would Vmax change? So we can see that T, right, or period, right? This is saying period's doubled without changing amplitude now. So it's opposite up here. Here, amplitude was doubled. Period wasn't changing. Here, period's doubling, but amplitude isn't changing, right? Well, we can see period, right? We said this already is based off of omega. So if period is doubling, right, we know that omega is doubling, or something must be, I shouldn't say omega is doubling. I'm sorry, that's not what's happening here. We know omega must be changing because period 2 pi, right, isn't changing. That's a constant. So we know that period is based off omega. If omega or if period's changing, then omega must be changing. That's what's changing period, right? And nothing's going on with amplitude, right? Which is what this is saying. So how would Vmax and Amax change? Well, we can, like we said before, right? The velocity max, right? And acceleration max, right? Both those equations, right? They're based off of amplitude and omega. Here, omega is or with amplitude, max acceleration. Sorry about that. With max acceleration, we can see omega squared, but with max velocity, we can see omega isn't squared, right? So we can see that when omega changes, as omega changes, it's also going to do something different in the max velocity versus the max acceleration, right? Here omega is squared, where here omega isn't squared at all. So what we need to do, if we know T is doubled, we got to figure out what is going on with omega. How is omega changing? Because omega is going to dictate the acceleration and the velocity. So we got to figure out what is the new omega. We got to find a new omega is what I'm trying to say, okay? Since we know if T is doubled, the only thing that could have changed is omega. What's that new omega? Once we have that new omega, we can put that new omega into these equations and see what's happening with velocity and acceleration, all right? So how do we do that? Well, we got to make a ratio. That's how we do it, right? So we know that, right, for our new, right, so I kind of marked these off. So this omega is the new omega that we're trying to find. This omega O is the original omega, right? So for the new omega, we know period's doubled, right? For the original omega, period was just period, right? So we start with these original equations. It's just this equation right here, written 2 times. It's just for the new omega, we have to double the period. For the old omega, we don't. And what we do is we solve both these equations for omega because we want to make a ratio out of our new omegas, okay? And to kind of compare and see what's going on with them. So when we solve these both for omega, this one we're solving for the new omega, this one we're solving for the old omega, we see that really omega and period just switch spots. So since this period's doubled, 2t is going to come down here, omega is going to come up. Here, omega and period will just swap, right? So here we get omega period just on the bottom. Here we see 2 times period on the bottom because period was doubled here, all right? Now that we have our new equations for omegas, we can now make a ratio out of them. When we make a ratio, right, we just put the new omega over the old omega, which means we also got these new equations that they're equal to will also be divided by themselves. All right, so when we make this ratio of old omega over new omega, that also means that we're dividing this, right? When we make a ratio out of these 2 things, we're also making a ratio out of these 2 things, right? So when we make a ratio out of these 2 things, we're also dividing these 2 things, all right? But when we divide these things, we know the thing on the bottom will just flip and we can multiply. So with this, right, for the new omega, we see the 2 pi over 2t, that's represented there. But here, we're multiplying by this one because when we make this fraction, if I have to write here, I'll do it over here, kind of off to the side. I don't want you to mix it up with that question there. But when we do this fraction, right, of the new omega over the old omega, we see that 2 pi over 2t will be, in a different color, will be divided by, this will be divided by this, right? The 2 pi over t. But when we have this, we know that we can take this bottom one and just flip it, right? So we can flip it. We can make it t over 2 pi, right? We can make this part, just this part right here, 2 over 2, and then multiply. And that's what I did here. So this t, right, this 2 pi over t, I flipped. I just did t over 2 pi and multiplied it by this top one, okay? So this is what we originally had, but since we have this, I can, this bottom part right here, I can flip and then multiply, which is what I did here. So here we see the original, right, the new omega, 2 pi over 2t, and here's the old omega, just flip t over 2 pi. So what we do is when we have this relationship, we see that the 2 pi's are going to cancel out, right? So we see these are going to go away, and we see that the periods are going to go away, leaving us with just this 1, 2, or really what it's saying is that this ratio of the new omega over old omega is going to be equal to 1/2. And then when we solve this, when we bring the old omega over, we get this new equation that's telling us that the new omega is going to be half of the old omega. Okay, so we went through some work there. Rewind it, listen, watch this again to understand how I got this new omega. Okay, it was through a ratio. Once I had the ratio equal to 1/2, I just solved this equation. Now I have an equation, right? The new omega over the old omega is equal to 1/2. I solved this equation for the new omega. When I did that, it told me that because the old omega is just going to come over here, which is what we see here, that the new omega is just 1/2 times the old omega. That's how I did that. Now that I have my new omega, I can now put it into my Vmax and Amax, right? So if the new omega is 1/2, right, when I put that in, 1/2 omega times A, we can see that since A isn't changing and since omega, the only thing changing here is omega and it's halving, that means Vmax is going to be halved because that's the only thing that's changing in this equation. So when T is doubled without changing A, we get this new relationship, we get a new omega, and we see that when T is doubled without changing A, that Vmax would be halved. Why is it halved? Because omega is half of the original, right? In the original one, omega had a certain value, but the new omega, when period is doubled, the omega is going to be half of the original when period's doubled. When it's half, that means the omega in the original is going to be halved, which means that whatever the Vmax was before would just be halved, all right? Now, since omega squared over here, that means that 1/2 that we put in there will also be squared. When 1/2 is squared, we get 1/4, right? 1/2 times 1/2 equals 1/4. So we put that 1/2 in there where we put 1/2 omega squared. The omega squared just stays there, right? But that 1/2, since that's a number and it's also squared, it gets squared, right? So 1/2 squared is 1/4. So we see that the max acceleration would be quartered, okay? So again, when t is doubled, without changing a, the max velocity would be halved and the max acceleration would be quartered, all right? If you don't understand why, go back and watch why. We had to get a new omega. Why did we have to get a new omega? Because we knew period was changing. And if period's changing, that must mean omega is changing. So we had to figure out how omega was changing to figure out how velocity and acceleration were changing, because velocity and acceleration are based off omega. All right, now, what if we now move on to this next question where we're talking about a pendulum of mass, right? It has a certain mass and a certain length, and it has a period of 4 seconds, right? What is the period if the length is shortened by 1/4? Well, we know the period for a pendulum is 2 pi times the square root of the length of the system over the gravity, right? So in order to get that, what we have to do is we have to first get the new L, because we weren't told it. We were just told length L, right? But we were told what period is. Period's 4 seconds, right? So what we want to do is we want to rearrange this equation for L, which is what I did right here. So this first step right here is this equation rearranged for L, right? So there's, right, now keep in mind, in order to solve for L, I had to square both sides because I need to get G out to bring it over, right? So when I square both sides, I got to square root that 2. So 2 gets squared, turns into 4. The pi gets squared, which turns into pi squared. But then that square root drops off. So G, nothing happens to G or L. They just lose the square root. And so what happens is G gets multiplied over, 2 pi comes down, and L stays put. So for the first step, right, we're just solving this equation for a new L. Why are we solving it for L? Because we got to get the new length. Once we have the length, or not the new length, I'm sorry. We got to get the original length. Once we have the original length, we can quarter that length, and then we can put it into the period equation again and solve for a new period, okay? So that's what we're doing here. So first, we got to solve for the original length. How do we do that? We just rearrange this equation for L, okay? And since we know t is 4 seconds. But keep in mind, since t needs to be squared, t turns into 16, okay? And that's what we see right here in this second step. So here in the second step right here, right, all I'm showing you is that t squared, right, which is 4, is going to be 16. G stays, that 4 and pi squared stays, okay? So this is still just L. I just wrote it with t squared in there, okay? And then what we see is 16 divided by 4. Well, what's going to happen? That 16 turns into 4, and that 4 disappears, right? Because 4 divided by 16 is 4, right? And then right after that, so that's the next step right there that we see right there, is that I'm just dividing 16 by 4, leaving that 4 on top, but that G and pi squared are staying put from the original. And again, this is still just L, okay? I think that might be throwing you off because it's throwing me off, okay? So I'm just going to rewrite this with the L over there. I just want it on this side. So this is L, right? This is the original L. Sorry about that. I see I had the L written over here, and that might not have been. So I rearrange this for L, right? It's the same thing. I just want you to know that, you know, when we move on to the next step, these are all still L, okay? When we move on to this is still L, right? When we go on to this is still L, okay? I'm just solving for that original L, okay? So here, once I've done the division here with 16 and 4, I'm left with just 4 times G over pi squared. Well, this is going to be my length, my original length, and so I want to go ahead and multiply that by 1/4 because I want to fourth it, right? They asked me, what if it's shortened by 1/4? Well, that's when, you know, 1/4 is, when we multiply things, that's a quarter, right? 1/4 is equal to 1/4. quarter. So when we multiply this length by a quarter, we're going to get the new length that we want to put into our new period equation, right? So when we multiply this by a fourth, we see that these 4's will cancel, and then all we'll be left with is g over pi squared. So what we solved for here, right, we used the original length, but what we got here at the end, right here at the end, let's do that in green, right? This is the new length. This is the new length, because how do we know that? How do we know that? Because we multiplied it, right? They said we had to shorten this by a quarter, so we multiplied this by a quarter, which was going to short. It gives us it's short, right? It tells us how this length will shorten by a quarter, okay? Because we're getting a fourth of that length, right? So what I'm trying to say is this is the original length after doing, right? We solved this equation for the original length, okay? By squaring both sides and bringing g over and 2 pi down, all right? But when 2 pi is squared, it turns into 4 pi squared, okay? The next thing we did is all I did was turn period, substitute period for 4, and 4 squared is 16. So this is still the original length, just with the numbers. Then I did some math and divided 4 by 16, which we can see that 16 will just turn into 4, and that 4 will disappear on the bottom. And so that right there is our original length, but now I want to take that original length and multiply it by a fourth, because I want to see what the period is going to be when it's quartered. So now I'm getting a quarter of the original length right here, right? And when I do that math, these 4's are going to cancel, and I'm left with this. So this length right here that I have here is the new length, the quartered length, all right? So I want to take that length and I want to put it back into this equation, right? And that's what I do here. So I rewrite this equation, but now I replace this L by g over pi squared, which is right there. And we can see that g just stays, so this L disappeared because that L turned into g over pi squared right there. But that g right there stayed put, all right? And then we can see that those g's will cancel. So we can see that the new period, right, the period of this pendulum, when the length is shortened by a quarter, will be equal to this. So you can just put that into your calculator, right? You know what 2 pi is, you know what pi squared is. You don't need any, there's no givens that you need from the question, so you can put that in the calculator and you can get period, all right? Okay, so question B says, what is period if mass is 2 times larger? If we double mass, well, we can look at period. Mass has nothing to do with it, right? It's the period for a pendulum is just based off the length and the gravity that pendulum's sitting on, so period isn't going to be impacted by mass, so the period isn't going to change at all, right? Period not impacted by mass, so the period won't change if mass is 2 times larger, okay? What if period of oscillation is increased 4 times? Well, again, period is in figure, so oscillation, right? What is period if oscillation is increased? Well, oscillation is going to be the amplitude, right? If we increase, let's say that we have a pendulum and we go from here, right? And then the next time we choose to bring it up this high, right? So if I have a pendulum and I bring it here, it's going to oscillate like this, right? But if I have that same pendulum and I bring it here, it's going to oscillate like this, okay? That's what it's saying. What is period if oscillation is increased 4 times? Well, period it's not affected by amplitude, right? That's amplitude. This, right, that's one amplitude, right? And this, that's another amplitude, right? That's a large amplitude. When we compare it to this, this is a small amplitude compared to this, a very large amplitude. And that's what they're talking about here. The oscillations increase, so that's increasing the oscillation, okay? If we increase that oscillation, okay, we can see that period's not impacted by that. Nothing would happen is what we're saying there, okay? All right. For this final equation here, or final question here, we have a wave is traveling on a stretched string that is 4 meters long, and it takes 2 seconds for the wave to travel back and forth. So it takes it to travel to the end, right? We have this string that's 4 meters long, right? 4 meters long, and the wave right? It takes 2 seconds for it to travel there and then back. Okay, that's what this is saying. Okay, a stretched string that is 4 meters long and it takes 2 seconds to travel back and forth. The wave takes right back and forth. Okay, so but we know the right. It takes 2 seconds to do that. So that means for just to get from one length of the string to the other, which is just the 4 meters, right? It's only going to take it a second, right? If it takes it 2 seconds to go back and forth, then just to go once is going to be half of that, right? So we know velocity, right, is displacement over time. Well, the displacement here, if we just look at, now we could do this 2 ways. I just looked at if the wave just moved once. So if the wave just traveled one length, which would be 4 meters, that would take it 1 second to do that because it takes another second to travel back. So 4 over 1 is equal to 4 meters per second. So the wave is moving at 4 meters per second. But let's say that you wanted to look at the 2 seconds. You said, okay, well, I want to see it in 2 seconds. Well, we have to look at the 4, right? Since it's going there and coming back, that means it's actually, the displacement's actually 8. Okay, because the length of the string, when it travels this way, that's going to be 4 meters, and when it travels back, that's going to be another 4 meters. So that's going to be 8 meters, but when it does that back and forth, it's moving in 2 seconds. So this is still what? 4 meters per second. So no matter how you want to look at it, we still get that the speed of the wave moving on this string is 4 meters per second. All right, now the last question here is saying if the wavelength is equal to 2.6 meters, what is the frequency? Well, we know frequency is equal to velocity over wavelength. We know the velocity, which is 4 meters per second. We know the wavelength, so it's just as easy as putting in this equation, and we get 1.5, which is, we know for frequency is hertz, so we know that this is 1.5 hertz. The frequency of this wave on this string is 1.5 hertz. All right, so again, these were kind of short little questions, but I just wanted you to understand how to use these things. They can be a little tricky, right? Where here we had to solve for a new omega, here we had to solve for a new length, right? But overall, they're not too difficult. So if you were confused here, again, go back and re-watch this video. Make sure you understand it. If you didn't understand where some of these things were coming from, then go watch the concept videos, because I do concept videos for all these. They're separate videos that I do concepts for all these, but I do concepts for all these. These two are going to have their own concept video, and this is going to have its own concept video. But go watch those and you'll understand where these are coming from, okay? Because that'll help this make sense if this didn't make any sense to you what I was doing here, okay? Well, I hope this was helpful, and I will see you on the next video.